Okay, physics class, how are you doing on chapter 20, electricity, terms and concepts for chapter 20? This last assignment. So we want to check your answers on most of these you could probably have found in the book. A lot of them you probably already kind of knew anyway. Like the first one, define electric current. This is one of the scientific words that, this is chapter 20 and 21 a little bit. Current, electricity. And so let's define current. It is a good term. A lot of times words, we don't know why they chose a word to describe something, but this is very much like water flowing, and except that it is the flow of charge. That's a good definition. Good enough. Charge, of course, we don't really know what that means either. We have words for things and we think we understand them. But that's what God has given us. He is a God beyond our understanding, and science is always incomplete in its comprehension and its terms and its understanding. But we can at least use this model to predict things and calculate things and engineer the myriad of devices that make this lecture possible, for that matter. The possibilities of communication in this time of the COVID-19. Well, what two things are required for electric current to flow? Just like if water is going to flow, there has to be, of course, a path for the flow, but it won't flow just on a path unless the path is tilted. In the case of water, it's gravity, a force that's pushing it. In the case of electricity, we say a potential energy difference, or potential difference for short. A potential difference. It is a difference in potential energy from one point to the other. In the case of water flowing downstream, it's a gravitational potential difference. Potential energy difference. This is sometimes they call that voltage, but we'll get to that in a sec. Give the unit definition for 1 ampere. 1 ampere. Well, that is the unit of current. The flow, 1 ampere is 1 coulomb per second. And of course, there we go, using another word that you're not familiar with, the coulomb. But the coulomb is the unit of charge, like the kilogram is a unit of mass. 1 coulomb per second, the ampere. A lot of the circuits in our homes, we hear people talk about a 20 amp circuit or a 15 amp circuit or an extension cord that may be rated 15 amps. A fuse can be rated so many amps. It's a rate of flow. If you get too much flow, you get too much heat because those flow of charges collide with each other and dissipate. We know, of course, by the second law of thermodynamics, it runs everything. And basically, it says that all energy must die. And electrical energy is the same. Give Ohm's law. Ohm's law. In a conductor, in a metal conductor, we would have to say, in a metal conductor, the current that flows is directly proportional to the potential difference, or the voltage. I'll write it out. Potential difference. Which is voltage. For sure. So yeah, just means if you double the voltage, you'll double the flow of current. If you push twice as hard, you'll get twice as much movement. That's not that much different than a lot of the mechanics that we've talked about earlier in the year. What effect does increased voltage then have on current? Increase. As a matter of fact, directly proportional. That's what Ohm's law tells us. Double voltage, double current. So let's talk about where does the potential difference come from? Where can we get a flow of current? How can we make current flow? How can we push on it? How can we push on a charge? Well, the only way to push on a charge is with another charge. Charges repel, like charges repel, opposite charges attract. And so these sources, well, we know where do we get electric energy? Of course, it's not the flow of charge that we're interested in, it's the flow of energy. Charge just carries the energy. You plug something in the wall. We think of that one first, maybe. That is electromagnetic. They actually use magnetic fields that are created by coils of wire carrying current. But you can also just use a plain magnet. Oh, man, I wish we were meeting it because there's so many demonstrations I want to show you. Like the old crank telephone generators, or they also use them to detonate explosives. It was a magnet that was spinning around a coil of wire, and I got one off the internet, and we hold on to the little paddle things and crank on that thing and get current to flow. Magnets can push on charge because magnets are created by moving charges. What if it's not plugged into the wall, but it still runs off of electricity? Well, we would think of batteries. Let's call them electrochemical cells. A battery is a word that refers to a series of things, including a series of electrochemical cells. So electromagnetic, electrochemical, what else? If it doesn't run off batteries and it's not plugged into the wall, it could run off of light. Photoelectric. And I've got some cool demonstrations about that too, where we're making electricity with light. We can actually send a little radio signal over a light beam to a solar cell, to a photoelectric device. Lots of different metals can produce a flow of electrons if they are struck by a certain frequency of light. Yeah, and we can actually send that radio sound and then recreate sound on the other side. It's kind of a neat effect. But you've seen the photoelectric effect many times. The motion sensors and the beams that trigger an alarm or the presence of something by the breaking of a beam of light. The other two are probably not as common. One is creating electricity by heat, the thermoelectric. The most common place in your home you'll find these is the thermocouple that keeps your furnace pilot light lit. As long as there's actually a flame that we call the pilot light, and there's a thermocouple that's in that flame. As long as that flame is heating up that thermocouple, electricity will flow, and that electricity then is what keeps the gas flowing to the home. If that flame goes out, the gas has to know not to flow into the room. So the thermocouple then quits producing electricity, and the gas then shuts off. A very clever idea for using the thermoelectric effect. But of course we use them all the time too to tell how someone's temperature by turning their temperature into electricity. So all the modern ways of determining body temperature is thermoelectric. The last one is also very common, but we don't hear about it much. The piezoelectric. Piezo is an Italian word for pressure. If you know of anything that you put pressure on and it creates a spark, like a charcoal grill lighter. You push the little trigger and you get a click sound and spark. But you may not know that that effect is also used in guitar pickups. Not electric guitar pickups, they're electromagnetic. They actually have little magnets and coils of wire. But acoustic guitar pickups are typically the in the bridge, and the vibration actually squeezes a little crystal. And when you squeeze on that crystal, it pushes the negative charges one way and the positive charges another way, and you create a potential difference because of that squeezing. You can use it in reverse. You can send electricity to the crystal, and you can make it move, which is common for every greeting card that sings to you. It actually has a piezoelectric crystal in it. Electronic drums. You strike something and it creates an electric signal. Digital pianos. The keys are actually triggered by piezoelectric effect. Very clever, very useful. It doesn't generate a lot of electricity, but it can generate signals that we use to control things. All right. Number 7. What effect does increased current have on, increased resistance have on current? Number 7. Well, what do you think about that? If you have every wire has resistance, but if you have more resistance, it would be like turning the valve on the garden hose down. Increasing the resistance decreases flow. That makes sense, I hope. Number 8. If 1 volt of potential difference is applied to a 1 ohm resistor, how much current will flow? 1 amp. That's the definition of an ohm, which is the next one. Give the definition of an ohm. It is 1 ohm is when 1 volt is applied and you get 1 amp of current flow. 1 ohm is 1 amp per volt. Or, whoops, that's the other way around, isn't it? 1 volt produces 1 amp. So R is V over I, yeah. 1 volt produces 1 amp. 1 volt per amp. So 1 ohm resistance, if you apply 6 volts, you'll get 6 amps. If you get 120 volts, you would get 120 amps on a 1 ohm resistor. It's just a way of defining the resistance of the path by the ratio between the potential difference applied and the current that results. Number 10. What effect does the increased length of wire have on its resistance? The longer the wire is, the harder it is going to be for the current to flow through. So it does increase, which is why if you have a long extension cord, it needs to be a bigger extension cord. A long, skinny extension cord has too much resistance. I know a kid that tried to trim the hedges with a whole bunch of little tiny 16 gauge extension cords from inside the house. He couldn't find the big power cord that his dad usually used, so he put a bunch of little tiny cords together and made a big long small cord. Too much resistance and too much heat produced, and the insulation dripped because it melted off of the extension cord. Number 11. What effect does increased cross-sectional area have on resistance of a wire? Well, if you get a bigger wire, increased cross-sectional area, bigger wires decrease resistance. So, and that's why you would have to compensate. If you're going to go a long ways with an extension cord, or wiring in your home has to go a long ways from the breaker box, then you need a bigger wire for long distance. It decreases resistance to increase cross-sectional area, inversely proportional then, but length is directly proportional. Twice the length, twice the resistance. Where are we? 12. What becomes of the energy that flowing charges have when they go through a resistor? Well, the whole point of electricity is the energy that it carries. So what happens to that energy when it goes through a resistor? It turns to some other form. Another form of energy. Like light, sound, motion, a fan or something mechanical that's moving. And of course, eventually, all energy turns into disordered energy, which is heat. So it could be, yeah, light, heat, sound. It turns into some other form of energy anyway. 13, how does the current after a resistor compare to the current before a resistor? Well, current doesn't disappear. If a certain current flows into a resistor, the same amount of current has to flow out of the resistor. It doesn't disappear. Unless there's a short to the ground or something that's connected, but that would be a different path. It's the same before and after. Same before and after. How does the voltage after a resistor compare to the voltage before a resistor? Now we're talking about energy. Voltage is how much energy the flow of charge has. So we just said what happens to the when it flows through a resistor, it turns into some other form of energy. Like this could be producing sound, that could be represent a speaker, or it could produce light, or it could produce heat. Well, of course, by the conservation of energy, then, if you got so much energy coming in, and it does some other form of energy, it turns into, then there's going to be less energy coming out. So it decreases the energy. Yeah, decreases. Also, we could call it voltage. It decreases the voltage. Resistors decrease voltage. 15. What unit results from multiplying current, which is 1 coulomb per second, multiply that times voltage? Did we define voltage yet? Oh yeah, that was the last worksheet. Voltage is 1 joule per coulomb. So if you've got amps, which is A, times V, which is volts, right? Look, the unit label, coulombs, cancels. The unit is joule per second. Well, we know what a joule per second is. We had that in mechanics. Watt is the unit of power, and a joule per second is a watt, right? 1 watt. Joule per second. Yeah, it's all very simple. It's just language that we have to learn. And 16, draw 3 resistors in series. Oh, 3 resistors in series. Well, let's do that. In series, that means one after the other, right? Squiggly lines. Pinky and the Brain. That was always a favorite cartoon. Pinky, do you understand what I'm saying?
Yes, and I particularly like all the squiggly lines.
A couple of mice, if you don't know them. We usually draw a big line and a small line to represent a source of potential difference. You see, potential difference, big, small. Very likely this could be the positive end of a battery and the negative end of a battery or something, right? Little knob there, plus, minus. Of course, Ben Franklin thought that positive things flowed from the positive end to the negative end. It's actually the negative things are flowing from the negative end to the positive end. But the equations are still the same. The model, one model works as good as the other. Neither one of them work perfectly. But anyway, resistors in series, one follows the other. It loses a little bit of energy here, loses more energy here, loses more energy here. So the total amount of energy that's lost, though, is whatever this battery would be, or whatever the voltage supply is. You can't have more loss than is gained or anything. You have to account for all the energy loss. Number 17, draw 3 resistors in parallel. Now, they don't actually have to be in parallel, but they would be one not following the other, but one next to the other, providing an alternate path. That would be alternate parallel resistors. And this could be the battery, big line, little line. Could be the 1.5 volt cell. Of course, if you can tell if Christmas lights are one of the labs we would do. When we hook them up in series and you take out one of them, the other two don't work because you've interrupted the only path. But if you take out one of resistors in parallel, the other two can still work. This was just an alternate path. So that's another way to test for parallel and series resistors. And 18. Kirchhoff's first rule, say the sum of the currents entering, that would be, think about that, entering and leaving a resistor. Well, we said, wouldn't the current going in and the current coming out have to be the same? You don't lose current. So if coming in is positive and going out is negative, and it's got to be the same, when you combine, when you add two numbers that are the same but they're opposite signs, you get 0, right? That's the answer. Yeah, must be 0. Give the equation for resistors in parallel. Resistors in parallel like this, they add up this way. If you took 1 over the total, it would be this 1 over the first one, which this could be the first resistor, plus 1 over the second one, like this one's the second one, and 1 over the third one. Kirchhoff's first rule. Basically says the sum of the total resistance, the reciprocal of the sum of the total resistance is equal to the sum of the reciprocals of the individual resistances. If you really want to impress the chicks, memorize Kirchhoff's first rule. What about the second rule? Say of all the voltage changes that occur in a circuit must be. Well, we kind of already mentioned it. It kind of makes sense. It's the law of conservation of energy in disguise. And that basically, if you take this voltage drop, which is happening here at this first resistor, and this voltage drop, which is happening at the second resistor, and this voltage drop, which is happening at the third resistor, all of those voltage drops can't be more or less than the voltage that was applied originally. So the total voltage changes have to be, again, zero. What does Kirchhoff's second rule say? That the sum of all the voltage changes in a circuit must be zero. Is that what you had on 18 and 19? If you had no answer on 18 and 19, I guess that would be correct, because the answer is zero. What is the, give the equation for resistors in series. Well, this kind of makes sense then. The total resistance for all of those is just the sum of each individual resistance. We got a flycatcher singing to us in the back. That's actually a bird clock that I have. All right, that's 19. And number 20. What effect does higher temperature have on the resistance of a wire? If a wire gets hot, or a battery gets hot, or a power amplifier, or whatever the device, your phone gets hot, it actually gets more resistance. Increase, which is a computer's, those are the things that slow it down. If you increase resistance, those signals don't move as fast through the circuitry. So keeping the thing cool isn't just for safety, it's also for speed. We want to keep the resistance low, decrease the temperature, decrease the resistance, increase the speed and efficiency. It's kind of a vicious cycle. When something starts getting hot, it'll get more resistance. Well, that'll make even more heat, which makes it hotter and make more resistance, more heat, more, and it'll create this vicious cycle of heat. What unit of electrical energy does the Light and Power Company use to sell electricity? Well, you would think that they would talk about the joule, because that's the unit of energy. But most people don't know electricity good enough to know how to calculate joules. Instead, now if you think about it, a joule is a watt times a second. A watt is a joule per second, right? So a watt is a 1 joule per second. You multiply that times seconds, you get joule, right? Seconds cancel. Well, that's too small of a unit. People would understand a watt second better than they would understand a joule, because they look on the appliance and they could see how many watts of power it takes. They could multiply it times how long they used it, and they would have how many joules. But they'd have to know how many watts, how many seconds. Most things use a lot more power than that. So instead, we substitute a kilowatt, and instead of for second, we substitute hour. So it's a kilowatt hour. Yeah, and it doesn't have a derived name for it, like the joule or anything. It's just a kilowatt hour. So if you look on the device, maybe your hair dryer, for example, if it says 1400 watts, that's 1.4 kilowatts. Little k for kilo, big W for capital, 1.4 kilowatts. You could multiply that. If you took an hour to dry your hair, that'd be 1.4 kilowatt hours. Most people don't take an hour to dry their hair. So Jocelyn Bennett might. She has a lot of hair. She's not even in physics, so I can't tease her. Well. Let's see, going on. And by the way, you can, a kilowatt hour is 1 kilowatt hour is, of electricity is about 7 cents, something like that. 7 cents per kilowatt hour. That's the electricity rate. It varies, of course, in location. But if you've got a 100-watt light bulb, that would be 1/10 of a kilowatt, and you operated that for uh, 10 hours. Yeah, 100-watt light bulb for 10 hours would be 1 kilowatt hour. It would only cost 7 cents. So check out your computer, see what the power right by the cord. It'll usually tell you what the power it requires. Multiply kilowatts times hours times about 7 cents, and that's how much it takes to run your computer for an hour. Let's look at this last table, and we'll be done. Okay, some terms. What's the term for force? Of course, the symbol is F. The unit label is newtons. Sorry, I was thinking ahead. Force, F, newtons, the unit label. Charge, the symbol, Q. Your book uses little q, I believe. It could be big Q. I've seen both. Little q, big Q. The unit label, Coulomb. C. I'll spell it out. Coulomb, Newton. The Coulomb's constant. If you remember, the equation is the force, which is equal to the product of the charges divided by the distance between them squared. So it's coulombs meters squared per. Oh, wait a minute. Let's get this right. I got to think of the equation. It's K Q1 Q2 over R squared. So K would have to be newtons per Newton meter squared per Coulomb squared. That's it. You'd have to move these terms to the left side of the equations, leaving K on that side. So it'd be newtons times the meter squared per Coulomb squared. Oh, that's the unit label, of course. The actual numerical value for it is 9 billion. 9 times 10 to the 9th. Newton meter squared per Coulomb squared. All right. That, of course, is kind of like the gravitational constant. We can use it to calculate the force of attraction or repulsion, because electricity has two flavors of charge between two charges. Electric field. Electric field symbol, we just call it E for electric field intensity. And the unit labels, it's how many newtons per coulomb. How much force there is per coulomb. Like in gravity, it would be 9.8 newtons per kilogram of mass. That describes the gravitational field of the Earth, at the surface of the Earth anyway. Electric field potential difference. The symbol for it, V, which is voltage. That's the unit label also, V, voltage. Energy, work, we know what that is. That's the joule. The symbol first. The symbol would be W, or energy for work. But the the unit label would be joule. And energy sold to consumers, though, we said, the power company doesn't use the joule, it uses the kilowatt hour. We'll put that here, kilowatt time hour. There's really no symbol for it, I guess. W would also be a symbol for work, energy, current, symbol I, and the unit label, coulomb per second. Power, of course, P for power, and the unit label, watt. Watt is the unit for power. Resistance, and we use the symbol R, and the symbol, the unit label is ohm. Hey, I've run out of room, and the others aren't really that important for high school physics anyway. There were some extras. Don't worry about them. Oh, there's a whole lot of fun jokes we can do with that symbol. I have to do at least one. We call them ohm jokes. Like, for example, if you put wheels on an ohm, it becomes a mobile ohm, right? Okay. You can think of some more on your own. I won't bore you with them. Okay, that concludes. Hey, let's have a prayer and thank God. Dear Lord, we thank you for this force again, this electrical thing that we still don't understand completely, but we have a few words that we can, and a model that we can use to describe it. Helps to appreciate it as we use electricity all during the day. The electrical power that runs things, and but also for the information that we send to each other over electricity. In Jesus' name we pray, amen.